Okay, it's Brian here. We've been talking about motion in chapters 1 to 3. And in chapters 4 and 5, we're going to introduce forces to the mix, okay? And they're very much related because if I have a change in motion, that is produced by forces. So what I want you to do is I want you to pause watching this video. I want you to go take a look at chapter 4 because the work that I'm doing here assumes that you have read chapter 4. So go read chapter 4, come back and take a look at this. We're going to talk about chapter 4, and we're even going to dip a toe into the waters of chapter 5. So go read chapter 4, come back, pick it up where you left off. Here we go. Now, the first law of physics that we're going to learn in this course is Newton's second law, and it's this thing right here. The acceleration of an object, and we know what that is. That's just equal to the rate of change of velocity, is equal to the net force acting on an object. This is the force in that law divided by the mass, and this is a law of physics. It is the other things we've talked about, velocity, that's a definition. Acceleration, that's a definition. But it just turns out the way our particular universe is put together, the acceleration of an object is related to its force by this relationship right here. And this is true in every circumstance we've ever seen. This is a law of physics. It is true. It is something you can take to the bank. And that's the first one we've seen in this course. Now in chapter 4, you had a chance to read about the short catalog of forces that we are going to consider in this chapter. And by considering these forces, we'll be able to model the motion of all kinds of objects. Forces are measured in the units of newtons, okay? And a newton isn't a unit you've used much. But it turns out 1 newton is about equal to 1/5 of a pound or so, 1/5 of a pound. So the weight of a 1 pound object is about 5 newtons. And you can use that to convert between pounds and newtons. And if you get an answer in newtons, put it in pounds just to see if it makes some sense to you. That'll help you do some assessments. Now in this motion and force chapter, we're going to be interested in telling stories. And what I mean by that is this. We are going to take any kind of a motion we look at, we're going to tell 2 stories about it. First off, we're going to draw a motion diagram. That's our motion story. And we're going to be interested in this moral of the story. What is the acceleration? And then we're going to draw a free body diagram to represent the forces. Once we've got all the forces, we're going to say, what is the net force? So we're going to be interested in that. And the thing that relates these 2 parallel stories of the forces and the motion is Newton's second law. The acceleration is related to the net force that acts on an object. And that's basically how we're going to set up every problem. We're going to write a story about the motion and a story about the force, and we're going to relate them using Newton's second law. Now let's take a look at a couple of the forces we're going to work with. The first one is weight. Any object near the surface of the Earth experiences a weight force. It is directed straight down. The magnitude is m times g. So Milo, wherever he is on the surface of the Earth, experiences a weight force directed straight downward. The magnitude is his mass times the acceleration of gravity. And his mass is about 24 kilograms. G is 9.8 meters per second squared. And so the weight force acting on Milo is about 240 newtons. So anytime I draw a free body diagram that includes Milo, my first thing I put in is a weight force directed straight downward. The magnitude is about 240 newtons. Now, just a quick reminder, the units of force that we're going to use are newtons. And it turns out pound is also a unit of force. And a pound is equal to about 5 newtons. And when you step on a scale, you measure your weight in pounds, but weight is a force. You can't directly convert between a weight and a mass, okay? Weight is a force. Mass is a different thing. Kilogram is a unit of mass. A pound is not. A pound as a unit of weight is a unit of force. You really can't convert kilograms to pounds. The unit of mass in the English system is the slug, which is kind of awesome. You can read more about this in chapter 4. Now, if you're standing on the surface of the Earth, there's a weight force which is directed straight downward towards the center of the Earth. And there better be an upward force to counteract that. Otherwise, you plummet towards the center of the Earth. And in most cases, that's the normal force. Now, the normal force is a contact force from a surface. And we call it the normal force because normal is just a synonym for perpendicular. And so the normal force is perpendicular to a surface. And if you're standing on the Earth, there's a normal force that is perpendicular to the surface of the Earth that points straight up, acting on you. If you stand on a scale, you have typically said, I'm sitting on a scale, I'm looking at the dial, and I'm reading my weight. But it turns out the scale does not measure your weight. What a scale actually measures is the upward normal force that it applies to you. So it is measuring how hard it's pushing upward on you. Now, under normal circumstances, if you're standing on a scale and you're standing still, there's a downward weight force on you. There's an upward normal force on you from the scale. But typically, you're not accelerating if you're standing still. And so as a consequence, the net force on you is equal to 0. And if the net force is equal to 0, the net force is the sum of the forces. The sum of the normal force and the weight force are equal to 0. So what that tells me is the magnitude of the normal force is equal to the weight force. So under normal circumstances, when you stand on a scale, the number that you read is your weight. But we're going to consider some other circumstances. In the homework, you're going to consider this case of a person who stands on a force plate, which is basically like a scale. And she's initially still, but then she pushes off. And when she pushes off, she is accelerating upward. She's accelerating upward. If she's accelerating upward, there better be a net force on her that is upward. So there's an upward force that is bigger than the downward force of the weight which is acting on her. So the normal force on her is bigger than the weight force. And you can see that on this graph. During the push-off, the normal force, which is the force provided by the force plate, is bigger than her weight. And in that case, she has a net force upward, and so she accelerates upward, okay? So the normal force isn't always equal to the weight force, and that'll be an important consideration for us when we solve problems. So when you look at this one, your first step is going to be to draw a free body diagram for each phase of the motion. So treat this problem as 5 separate problems. For each one, you draw a free body diagram, and they look like this. So go ahead, try that yourself. You can come back here and confirm that that's what you're getting. But these are the kind of free body diagrams you should be getting for those 5 phases of the motion. Now, if something is moving through the air or moving through the water at a speed v, there's a drag force that acts, and it is parallel to the velocity, but is also opposite the velocity, is opposite the direction of the motion. The magnitude of the drag force is 1/2 times the drag coefficient times the density of the air or the water times the cross-section area of the object times the square of the velocity. Lots of numbers. But the drag force is really interesting to us because we're going to be very interested in locomotion. And I want to consider animals that move in the air and animals that move in the water. And in both of those cases, the drag force is very, very important. So this equation will be an important one for us. And let's look at an example of a problem using the drag force. And here's an example that's similar to the type of thing you're going to see on the homework assignment. On the homework assignment, you're going to see a whole bunch of problems where the question is asking you, or the problem is asking you, to just draw a motion diagram and a free body diagram. You don't draw, or you don't do any calculations. And so in this case, basically what we're doing is strategizing and preparing. There's no solving, and just, so there's some assessment. And so you can just do strategize, prepare, and then do an assessment. No solving this time. No solving this time. When you are actually solving problems, it's vitally important that you draw the motion diagram and that you draw the free body diagram. And so we're going to give you practice for this with this. And so the first assignment, we're basically just drawing the pictures. So Skydiver has jumped from an airplane. We're going to draw a motion diagram and a free body diagram for 3 segments of the motion. First, the Skydiver is speeding up. Second, the Skydiver has reached terminal speed. Third, the Skydiver has just opened her parachute. And let's do those in turn. So Skydiver is speeding up. Skydiver has jumped out of the airplane. The points on the motion diagram are getting farther apart. The velocity vectors are getting bigger. So as a consequence, there's an acceleration, and the acceleration is directed downward. Now, if that's true, there must be a net force which is directed downward. And if the net force is directed downward, my free body diagram looks like this. Skydiver moving through the air has 2 forces acting on her. Weight force, which is always a thing, and drag force. But the weight force is acting downward. The drag force must be smaller because the net force has to be directed downward. And so I'm going to look at that. My assessment is, oh, the weight force is bigger than the drag force, which means there's a net force downward, which means the skydiver is accelerating downward, and the skydiver is, in fact, speeding up. Boom. Now let's get rid of those diagrams and do the next one. And the next one is this. The skydiver has reached terminal speed. And terminal speed means she is not speeding up. So her motion diagram looks like this. It's a series of dots that are evenly spaced. So the velocity vectors are the same size. The acceleration is equal to 0. If that's true, the net force is equal to 0. So that will help inform how we draw our free body diagram. Well, the weight force is acting downward, but there's also an upward drag force, and I'm going to draw it exactly the same magnitude as the weight force because we know the net force must be equal to 0. So at the situation of terminal speed, the weight force and the drag force are equal. The net force is 0. There is no acceleration. And there's no acceleration. My assessment is that's perfect because she has reached terminal speed. And that's the definition of her terminal speed. She is not speeding up anymore. Now let's get rid of those and think about the third phase of the motion. So in the third phase of the motion, when she opens her parachute, let's think about her motion. And her motion, she's going to be moving quickly, but she's slowing down. That's the point of the parachute, is to slow you down. So her velocity vectors are pointing downward, but they're getting smaller. That's a net acceleration that is upward. The acceleration is directed upward, which implies there is a net force directed upward. Since there's a net force directed upward, if I look at the two forces that act on her, there's a downward weight force, and there's an upward drag force, and the drag force must be bigger than the weight force to give me a net force which is acting upward. My assessment is drag force is bigger than weight, which implies that there's a net force upward, which implies that there's an upward acceleration, which implies that she is slowing down. Exactly right. And also, too, the drag force is bigger because we know the drag force is proportional to the area. And when she opens her parachute, the area gets bigger, and so we expect the drag force to get bigger, and so everything works out like planned. And here's a kind of a more careful version of these three motion diagrams and free body diagrams for your consideration. Now there's also a lift force. When things move through the air, you have a force which is parallel to the motion but opposite it. That's the drag force. The lift force is perpendicular to the velocity, okay? And that's something we will be interested in. Now we want to take a look at contact forces, okay? So suppose I have a box which is sitting on an incline. Well, we know there's a downward weight force acting on the box, but the box isn't accelerating. The net force is equal to 0, so the incline must be providing a force that is directed straight up. But you know, in physics, whenever we have a kind of a complicated situation, and this is pointing at some weird angle, I want to make it simpler by just taking this force straight up and turn it into two components. And we're going to get a component that is parallel to the surface and a component that is perpendicular to the surface. Now the component that is perpendicular to the surface, that's the normal force, okay? And that is due to molecules in the surface that are resisting compression. The box is pushing in on those molecules. They are pushing back. That's the normal force. But there will also be a component parallel to the surface, and that's what we call the friction force. And that is due to molecules resisting sliding. They're trying to slide over each other, but it's a microscopic scale. The molecules are grabbing a hold and resisting the sliding. And that resisting of sliding due to the molecules in the surfaces is what we call the friction force. Now, whenever I have two objects in contact, I get these kind of forces. So when you're walking on the ground exerts two forces on you. There's a normal force perpendicular to the ground, and there's a friction force parallel to the ground. And when you're walking, the friction force is the thing that propels you forward. It has to be, because the force propelling you forward is parallel to the ground, and we know that the force parallel to the ground is the friction force. Imagine you were trying to walk on really, really, really slick ice where there's no friction. You're not going anywhere. It's the friction force that moves you forward. Couple of facts about the friction force. We are typically going to be interested in the static friction force. That's what exists when objects aren't sliding. The static means no sliding. And the static friction force has a maximum value. The biggest it can be is μs times n. It is always less than or equal to that. If surfaces are sliding, the force that exists is a constant, and it's just equal to the kinetic coefficient of friction times the normal force. And you can read more details about that, of course, in Chapter 4, which you have, if you haven't read Chapter 4, go back and take a look at the section on friction. So let's take a look at another example. And this is the type of thing you might be expected to do for this week's homework assignment. A frog is pushing off the ground. It's launching itself at a 40-degree angle. Okay? Its feet are in contact with the ground, and it is speeding up. The contact forces are much larger than the weight, and we're going to assume that we can ignore the weight, this force, i.e. the weight force. We don't have to worry about it. Under that circumstance, we are asked to draw a motion diagram and a free body diagram. What will those look like? So again, it's one of those problems where we're just asking you to strategize, prepare, and then assess. No solving this time. And so the problem is just asking us to draw a motion diagram and to draw a free body diagram. And so basically, we're not doing any solving. We're basically doing the strategizing and the preparing and then the assessing. The strategizing is to say this. I'm going to take a look at the type of motion we have. The frog is speeding up. Since it's speeding up, that tells me there is motion with acceleration. Okay, that's my strategy. And that also tells me there is going to be a net force. But now I'm going to get down and dirty and do the prepare step. And my prepare step is basically to draw these pictures. Okay, so here's my prepare. My prepare is to draw pictures. My two pictures are a motion diagram and a free body diagram. The motion diagram looks like a series of dots that are getting farther apart. The frog is moving in this direction and it is speeding up. And so there is an acceleration that is directed this way. If that's true, there's also a net force that is directed this way. I know that that has to be true. But I also know that the forces on the frog come from the surface, and there are only two forces that can come from the surface. There's normal force, which is perpendicular to the ground, and a friction force, which is parallel to the ground. And it's going to be static friction, because the static friction is, we assume the frog's feet aren't sliding. And we have ignored the weight force in making this diagram. And my assessment is going to be this. Hey, if I look at my diagram, if I draw a vector sum of the normal force and the friction force, I get a force that's in the direction of the acceleration, which it must be because the net force must be in the direction of the acceleration. So my assessment is that my drawings that I've made are consistent with each other. That's my assessment. And you always want to do something where you look back at your problem and assess it in some way. And here's some more careful diagrams of this. The frog is accelerating like so. It is speeding up. There's an acceleration in this direction. There's a net force in that direction, but it's produced by the upward normal force and the friction force, which are acting parallel to the surface. But if I do a vector sum of those two, I get a net force which points in the direction of the acceleration, and it also points along the frog's body. And we're going to see lots of cases where that's true. Typically, when an animal is doing locomotion, the sum of the ground forces, i.e. the normal force and the friction force, point along the axis of the animal's body. And we'll see other cases like that. And that is everything I want to talk about today, but we are not done with this material yet. I will have one more set of annotated slides where we do some more motion and force problems.